When we look at the Milankovitch cycles, we're going to be studying long-term climate factors as a result of Earth motions. When we look at eccentricity here, we're talking about the shape of the Earth's orbit. When we study obliquity, we're looking at the axial tilt. And when we look at the direction of the axis change, in this case the precession, it's really looking at the wobble of where the North Pole is pointing, that these cycles, that these variations change the amount of solar energy reaching the Earth. These are called Milankovitch cycles. They are named after a Serbian mathematician named Milankovitch, and who used them to explain an advanced retreat of polar ice caps. Essentially, we're looking at glacial ice ages. Many scientists believe that these play a critical role in Earth's climate. In this activity, you're going to learn about eccentricity, obliquity, and precession, and how they change through time. You'll also learn how these changes influence the Earth's climate. So, moving on. So, eccentricity is a measure of how elliptical an orbit is. A planet's closest approach to the Sun is what we call perihelion, and its furthest distance is what we call aphelion. So, perihelion, closest distance; aphelion, furthest distance. The eccentricity is a measure of how different these are. So, it's kind of a ratio. It's aphelion minus perihelion divided by aphelion plus perihelion. So, when E is equal to 0, the orbit is circular, perfectly circular. As E gets close to 1, the orbit becomes more elongated. When E is greater than 0, note that the Sun is not the center of the ellipse. So this will be our Sun, and this would be an example of Earth. Here we have perihelion, here we have aphelion. So Earth's eccentricity here, if I look at my values here, I can calculate it, but it's actually provided on the screen, so I'll just read it. Eccentricity of the Earth is 0.017. The eccentricity of Mars is 0.094, and the eccentricity of Pluto is 0.244. So you'll see that the Earth's orbit, or in this case the eccentric value, is actually, it's fairly circular, where Mars is a little bit more eccentric and Pluto's is actually the most eccentric of all the planets, even though it's been demoted as the dwarf planet. So eccentricity cycles. These eccentricity cycles follow about a 100,000 year cycle. The eccentricities vary from a minimum of 0.0005 to a maximum E value of 0.0607. The larger the eccentricity, the greater the difference in solar radiation that reaches the Earth at perihelion versus aphelion. At its current value of E equals 0.017, this difference is 6.7%. It is thought that over the long term, these changes can affect Earth's climate. So a little clear animation here for the Milankovitch cycle is that over a period of about 100,000 years, the shape of the Earth's orbit gradually changes from circular to elliptical. And that's what we're seeing here. Notice, perihelion and aphelion, this number, this value is going to change, so therefore so does the E value over large scales of time. So the second of the Milankovitch cycles involves obliquity. Obliquity refers to the tilt of the Earth's axis relative to the plane of its orbit. This tilt currently is 23.5 degrees. In December, the axis is tilted away from the Sun. The northern hemisphere receives energy from the Sun at a more oblique angle and thus results in winter. In June, the axis is tilted towards the Sun, and therefore the northern hemisphere is receiving much more energy because it has a less of an angle in which it's angled at. In other words, it's much more direct. And this results in summer weather. If the obliquity were 0, there would be no seasons. It would be like one homogeneous day, calendar year. Distance from the Sun is not a factor when determining seasons. So let's look at obliquity. If this would be energy from the Sun, we could look at this, and if we notice that in December, if this were the 23.5, here's our axial tilt. Southern hemispheres in the summer, northern hemisphere based on this picture would be in winter, and therefore 6 months later, different location in its orbit, the northern hemisphere is tilted towards the Sun, so it's in summer, and the southern hemisphere is tilted away, therefore it's in winter. So looking at this, the time of year, and based on the Earth's axial tilt, as it travels or orbits the Sun, we're getting changes in its location, therefore we're going to get changes in the directness of sunlight, which is what we call insolation. So here we see the obliquity cycles. The obliquity for the Earth's orbit follows a roughly 40,000 year cycle. This variation is going to be around, let's just say around 21 degrees to about 24.5 degrees. The larger the obliquity, the greater the difference in seasonal temperatures. So in this animation, the obliquity is exaggerated just to kind of show you what's happening with this axial tilt change. So if I interpret this graph here, these ebbs and flows, this up and down oscillatory pattern, really the obliquity is going to change over large periods of time. And we can see how they reach these maximums and minimums. The minimum here is 24,000, and the maximum, so here's my minimum and here's my maximum in 12,000 year increments. So here we can view the Milankovitch cycle here with the present axial tilt. Oop, I don't know what just happened. Let me reset that. So at present, Earth's axis tilts with respect to the plane of its orbit at 23.5 degrees. So we know this much. And as we change throughout the course of the year, the high latitude regions receive less solar energy than low latitude regions based on the directness of sunlight. So we have seasons because the axial tilt is not perpendicular to the plane of orbit. And because of this, the amount of sunlight received in an area varies throughout the year. So this is showing you the axial tilt in the Earth's relative location. So Milankovitch calculated that the angle varies between this 21, 22 degrees and 24.5 degrees in roughly 40,000 year increments. So the amount of sunlight at a given point is going to vary over time as well. And that's a key feature here, that any one individual Milankovitch cycle is going to have its own timeline, but when you put them all together, they will all coincide together at large scale time increments that lead to climate changing factors. So let's look here at the last one. And the last of the Milankovitch cycles is called precession. The Earth wobbles like a spinning top, which is running down. This wobble follows roughly a 20 to 25,000 year cycle. The Earth's axis now points at Polaris, our North Star. But every 13,000 years, right, halfway through its total cycle, it points toward the star Vega. So precession is caused by the gravitational effects of both the sun and the moon. So we're kind of playing this like tug of war of gravity. So if I look here at these precessional values, these oscillations here, you're going to see this alternating feature and factor here. And we could calculate this in terms of times a year. So my x-axis here is time, and this would be my precession value. But if I look at this picture, I'm simply trying to view that the North Pole is going to be pointed at different locations in the night sky. Therefore, all total, when you put all of these Milankovitch cycles together, you're going to get these compounding effects, particularly when they all constructively interfere with all of their patterns to where they all influence and decrease the amount of sunlight energy reaching the Earth's surface. So the Milankovitch cycle. So the third part, precession, this axis, this wobble like a top, is at roughly 25,000 year increments. This determines the timing of the seasons relative to the position of the Earth along its orbit. So really what we're looking at here is this changing feature, right, in about 25,000 year increments. And it's going to be pointed at currently Polaris, and in 13-ish thousand years, it's going to be pointed at Vega. And that changes the timing of the seasons. So the precession and eccentricity. So winter in the northern hemisphere at perihelion, there's more total energy from the sun, right? So this would be, this would be the southern hemisphere summer, and the northern hemisphere would be winter, right? Winter in the northern hemisphere. So precession changes the direction of tilt of the Earth's axis relative to aphelion and perihelion. Currently, the northern hemisphere experiences winter when the Earth is closest to the sun. 13,000 years ago, winter occurred in the northern hemisphere when it was furthest from the sun. So since most of Earth's landmass in the northern hemisphere, these changes are believed to have an effect on the accumulation of ice and snow at the poles and may play a role in the Earth's long-term climatic cycles and ice ages. So really, once again, we look at these in December, here's where it's located. In June, here's where it's located. But 13,000 years ago, right, when our precession value was different, notice that these changed. That here's the summer in the northern hemisphere at perihelion, and this would have been winter in the northern hemisphere at perihelion. So 13,000 years ago, look at this. Our northern pole was actually pointed toward Vega and not at where it is currently pointing at here we go, at Polaris. So it changes the timing of the winter in the northern hemisphere having a greater land mass than water mass, It just changes how the planet behaves and responds to incoming solar radiation. So let's look at this graphically. Insolation and climate. The Milankovitch cycles result in long-term fluctuations in the energy that reaches the Earth. There is good evidence that these changes in insolation have influenced the Earth's past climate. However, alone, these changes are insufficient to explain past climate. Other complex feedback effects are also important, and we can identify positive and negative types of feedbacks. The two graphs on the right show changes in insolation at 65-degree north latitude in global temperature difference from modern estimates using deuterium isotopes from the Vostok Antarctic ice cores. So if I look here, where I see these ebbs and flows, these peaks and valleys of where I find high and low temperatures, they also correspond to insolation values, right, in watts per meter squared. So where I get this higher value of insolation, I get these higher values of temperature, right? And that should make sense, right? And they're close. They may not be perfect, but they're pretty darn close, that they coincide with one another. But when you put these all together, it's the data you're looking at. You're looking at these Milankovitch cycles all together can add up to causing long-term, large-scale climate change.